Section 7.3. Alright, let's go ahead and look at an example. The purchase prices of all 55-inch HD TVs sold have a mean of $1,282 and a standard deviation of $305.19. So let's go ahead and label these numbers. Notice this says it's the purchase price for all 55-inch HD TVs. That means when they label this as the mean, that's the mean of all, or the population mean, so this is mu. And this standard deviation is also for all such TVs, so this would be the population standard deviation, or sigma. And now they're asking us to determine the mean and standard deviation for all possible sample means from samples of size 20. When they tell us the sample size is 20, they're telling us that n is 20, so that'll be important as we move along. Turns out, though, it's not that important for this particular part. When they ask you for, well, it is for the standard deviation, sorry. For the mean, though, it's not. For the mean of the possible sample means, first we need to translate that. The mean of the sample means would be the mu of the x bars. And the formula on the previous page that we just came up with says the mean of the x bars is always equal to mu. And up here we know that mu is 1282. So that part doesn't depend on the sample size. But when they ask us for the standard deviation of all possible sample means, that's the standard deviation of the sample mean, so the standard deviation of x bar. Our formula on the previous page says that should be approximately sigma over root n. We know sigma, 305.19, and then we divide that by the square root of the sample size. So the sample size does figure into the standard deviation of x bar. And then we'd go to the calculator for that part. So 305.19 divided by the square root of 20, and we get about 68.243. I feel kind of silly going out to the 3 because with money we'd normally stop at 2 decimal places, but this is also a standard deviation, and for standard deviations we want to put at least 5 digits, so 1, 2, 3, 4, 5. Alright, let's go ahead and now put these two numbers to use. What is the expected error when using the mean from a random sample of size 20 as your estimate? Well, in section 7.1 and 7.2 we said that the expected error for p hat was less than 2 standard deviations of p hat. We get the same thing here, that the expected error for a sample mean problem is less than 2 standard deviations of x bar. So it's the same idea as in the previous sections, it's just we're using the standard deviation of x bar instead of the standard deviation of p hat. So the expected error that I'd expect if I were to do such an estimate would be less than 2 times 68.243. And if I do the doubling there, I get that the amount of error I expect to get is less than 136.486. And that would actually be money. Again, kind of weird to have the third decimal, but I'm just doubling what I have here. But that says if you went out and you were trying to estimate the average price of all 55-inch HD TVs that are sold, and you did your estimate based on a random sample of 20 such TVs, you wouldn't get a perfect answer, but you would expect your error to be less than $136.49 roughly. Now, suppose that we use the mean from a random sample of 20 such HD TVs as a point estimate for the mean of all such HD TVs. Would it be unusual for the error to be over $100? Well, the expected error is anything under 136.486. So a value like 110 would be expected. An amount of error of $110 would be expected, not unusual. Remember, expected and unusual are complements of each other. And so, would it be unusual for the error to be over $100? I would have to say no. For example, an error of $110 is more than 100, but less than 2 standard deviations away from the mean. So in order for us to say that any such error would be unusual, it would have to be the case that any time your error was over $100, it would be unusual or more than 2 standard deviations away. But here's an example of $110. That would be an error that's too much, more than $100, but it's still less than 2 standard deviations away, because we know that 2 standard deviations away is $136. Alright, let's go ahead and take a look at some changes to this. What's the expected error when using the mean from a random sample of size 85? So one of the things I like to usually put on this as context is that there's this idea that somebody has hired us to make the estimate for the average price of all 55-inch HD TVs, and they're going to only pay us if we have an error of less than or equal to $100. So if the error is over $100, we don't get paid. So this is really bad news right here, because it says it would not be unusual for us to do all our work and still not get paid. So we shouldn't be happy about that. So one of the things we could do is try to increase our sample size up to 85 and see if that gives us a better chance of getting paid. So if n is 85 now, then that changes some things. It doesn't change the mean of the x-bars, but it does change the standard deviation of the x-bars. That'd be sigma over root n, or approximately sigma over root n, and the original sigma was 305.19 divided by the square root of this new sample size of 85. Let's see what that would be. So 305.19 divided by the square root of 85 gives a standard deviation of 33.103. So what's our expected error now? The expected error is always less than 2 standard deviations of your statistic, which in this case is x-bar. So less than 2 times, let's just go ahead and write that out, 2 times sigma x-bar, and that means the expected error is less than 2 times 33.103, and that means that the expected error would be anything less than, let's see, if we double that, 66.206. So here's the important thing to see. If we use a sample of size 20, it would not be unusual for us to get an error of like $110, and that's more than the 100 that the boss wants, so we don't get paid for that, and that's not even a surprise. But if we did a sample of size 85, then we would expect our error to be less than $66, which would therefore be less than 100, and we would get paid. And now, in fact, would it be unusual to get an error over 100 if you use the sample of size 85? Yes, because that would be more than 2 standard deviations worth of error, and in fact it would be very unusual, because if you triple this you only get $99. So to get an error of over 100 with a sample of size 85, that would be over 3 standard deviations away from the mean. So that would be very unusual. And if I was doing a job hoping to get paid, I would not like it to be unusual, I wouldn't like it to be expected that I don't get paid. And I would in fact like it to be very unusual that I don't get paid. So increasing that sample size reduces your error that you expect, and that means you have a better chance of getting a satisfactory answer, and therefore a better chance of getting paid. Okay, on the previous page I said using that sample size of 85 gives us a better chance of getting paid. So what if we looked at that specific question, what is the chance that we would get paid? So we get paid if we're within $100 of the truth. That's my hypothetical, and the truth, the real mean, was $1,282. It said that was the mean for all TVs. So if you go $100 under that, that'd be $1,182, and $100 over that would be $1,382. So if I get an X bar that's in between those, then I'm going to be within $100 of the right answer, and I'd get paid. So here's a possibility for how I could calculate that probability. I'd draw a bell-shaped curve for x bar. I'd put the mean of the x bars that we calculated as 1282. I'd put these boundaries of 1182 and 1382 on the picture. I would shade in the middle and try and find that area. So then I would go to get z-scores. So the z-score for this one would be 1182 minus the mean of 1282, and that's actually the mean of the population, but remember that's also the mean of x bar. And then I would want to divide that by the standard deviation, but since this is a probability question about x bar, I don't want to divide by sigma, which was 305.19. I want to divide by the standard deviation of x bar for samples of size 85, which we calculated to be 33.103. So that's what I'd put in the denominator. And then let's see what the z-score is for that. So I have 1182 minus 1282, which actually is just negative $100, and then divided by 33.103. So that should go into $100 a little more than 3 times. And because that's to the left of the mean, it's negative, so negative 3.021. If I did Z2, that's the same distance away, but just on the other side. So that one would also be 3.021 standard deviations away, just to the right. So that one would come out positive instead of negative. And then I'd want to find the area in between those two. So for the area in between, I would do normal CDF from negative 3.021 to positive 3.021. And by the empirical rule, if I went from negative 3 to 3, that'd be 99.73%. So that should be maybe slightly more than that here. Normal CDF from negative 3.021 to positive 3.021. And I get 0.9975. So if everything is done correctly here, then if I took a random sample of size 85, I would have a 99.75% chance of getting paid. However, it turns out there's a very big problem with the calculations that I've made, and I want to show you what that is. I used the normal CDF because I drew a bell-shaped curve. I would draw a bell-shaped curve if I knew that the distribution of x bar was normal, but there's nowhere in this problem that said x bar is normal. So this is the way I would like to do this work, but is this the answer? This is only the answer if x bar is normally distributed. And it does turn out that x bar is normally distributed sometimes and not normally distributed at other times. And we don't know whether this is one of those times. So right now I have to put a big question mark over all of this. But when we get done with the next section, we'll know what those conditions are, and we would be able to finish a problem like this off. So for now, knowing the mean and standard deviation helps us to calculate things like the expected error. But it doesn't yet allow us to do area, because for that we need to know shape, and that's coming in the next section. Alright, let's go ahead and wrap up this section by summarizing some of the key points that have been illustrated in our examples. First of all, when you're trying to estimate mu by x bar, it's typical that the probability of x bar being exactly equal to mu is approximately 0. This is very similar to what we had in 7.1 and 7.2, where we said that probability that p hat would be equal to p is approximately equal to 0. And the main point there is that when you're using a sample to estimate a population value, you don't have much chance of getting that exactly right, so you expect some sampling error. So let's look at some of the other points. The fact that mu of x bar equals mu is good news for estimating, because it tells us that all of our guesses, which are x bars, are centered around the value we are trying to estimate, which is mu. So we may not get the right answer and we're going to have sampling error, but at least sometimes we miss high and sometimes we miss low, and the average of our sample means is mu. So our guesses have the right answer surrounded. So we're going to miss, but at least we'll be missing sometimes high, sometimes low. And added good news comes from the statement that sigma x bar is approximately sigma over root n, because this tells us that all of our x bars will get closer to their center, which is mu, as the sample size we choose increases. So not only are we centered around x bar, but as our sample size gets big, our guesses are getting closer to the right answer. So we may not get right answers, but they should be close if our sample size is big enough. So if we increase our sample size, we'll make all the x bars get closer to mu, and that means the specific x bar we randomly choose will probably be a good estimate of mu. But the one piece that's lacking is we still need to know the distribution, we still need to know the shape of the distribution of the possible values of x bar, because even though we see from these two bullets that our guesses are getting closer and closer and better, we still want to talk about the chance of getting paid, and we can't do that until we know that we have a bell-shaped distribution. So as we move on into section 7.4, we're going to learn the conditions under which the shape of the x bars turns out to be bell-shaped, but for now we don't know those.